So let's get started. Good morning. Are there any questions before I start? Any? Yes, thank you. I sent an email out last night because of the juxtaposition of the walkout being in the middle of the lab sections. I thought it would be best if we just moved it to Tuesday. So it's still the same material. It's just the following week in your Tuesday lab section. Yeah, right. The TAs are still obligated to teach their section, right? They're employees of the university. You can ask them what they're going to cover. So last Monday, well, this is 2 times in a row where I have wanted to wind up the lecture with the solution to Pascal's and Fermat's problem and have run out of time. So I thought I would start today with that solution to make sure we don't run out of time. So just to refresh your memory as to what the problem is, so this dates back to the 1650s, and a gambler posed this question to Pascal, and over the course of 3 years, he had a correspondence with Fermat about how to solve the problem. And they solved it in 2 different ways. So here's the problem, and then we'll see how the way they've solved their 2 different solutions are the same techniques that we are using that we've introduced in terms of solving probability problems. So each player has a number. One is player A has number 2, and player B has number 6. And a die is rolled, and every time the 2 shows up, player A gets a point, and whenever a 6 shows up, player B gets a point. And if a 1, 3, 4, or 5 shows up, neither of them get a point. And the first to get 3 points wins the game. They've each staked 32 pistoles on the game, so there's a pot of 64. And the game gets interrupted, and it gets interrupted when player A has 2 points and player B has 1 point. And the question is, how should they fairly split the pot of 64? All right. So here's Pascal's solution. So he essentially uses a probability tree. He says if the game continued 1 more round, if A won, he would take all 64 pistoles. If B won, the game would be tied, and it makes sense that they would split the pot in half, and they'd each get 32. Now the chance of A winning on the next round is a half, and the chance of B winning on the next round is a half. So half the time A wins and he gets 64. The other half of the time it's tied, and it makes sense that they would split the pot. So his logic, therefore, is that A for sure will always get 32, no matter what the outcome is. And half the time he'll get an additional 32. So he should walk off with 32 plus half of the additional 32. 32 plus 16 or 48. Okay? Are there any questions on Pascal's solution? So he just plays the game 1 more round and says either A has won or they're now on equal footing. All right. So Fermat solves it differently. He says, no matter what, the game will be determined in 3 rounds. And so he looks at all the possible ways of 3 rounds happening. So it could be that in the next 3 rounds, the number 2 shows up all 3 times. A, meaning A wins, a point. Or 2, 2, and 6. So A wins, a point, and then B. Or A, B, A, B, A, B, 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 A, B, 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 A, B, B, B. All right. Actually, did I need to go that far? Is there, did I need? Yeah, it looks like I did one extra round, didn't I? Yeah. Thank you. So it would be decided in 2 rounds. But the point is that each of these is equally likely. They're the same length sequence. They're each equally likely. You count up the proportion where A wins, and that's 3/4. And the proportion where B wins, that's 1/4. Therefore, player A should get 3/4 of the pot, and B should get 1/4 of the pot. So again, it's 48 versus 16. Yes?
How is ABB different from BBA? Because they both end up with 2 winners.
How is ABB different from? Oh, very different. This is in sequence. So right now, when we start this is already going into the game where player A already has 2 points. And yeah, so it's starting from the point where player A has 2 points and player B has 1. And therefore, as soon as A gets a point, player A wins. Whereas B needs to get 2 points, and essentially B needs to get 2 points before A gets 1. You might ask, so I think one of the problems that some of you had was that you just played out the game until either A won or B won, and you had 7 outcomes, possibly. Maybe that's where you got your 7s, I'm not sure. But the reason why, so if you look at the first one on the left, we have A followed by A, and you might think, well, as soon as A gets a point, he wins, why continue? The reason why we're continuing is so that we can look at things that are equally likely, because if we stopped after 1 round, then if some of these were 1 long and others were 2 long, they would have different probabilities. So we sort of pretend to continue the game for an equal number of rounds and then determine who has won. And that's why I got a little confused and I put 3 rounds up instead of 2 rounds. So which of the techniques did you use or did they use to solve the problem? Fermat essentially used a counting technique. He listed all the possibilities, but he was a little, he also used some sort of special, he used a counting technique, but he made sure that everything was equally likely. So he said, well, I'm going to extend the game to make sure that I've got the same number of rounds so that I can use the counting technique. Neither of them, I believe, used the complement rule. Pascal, in essence, used trees. And in terms of the equivalent problem, they both used that notion where they said, it doesn't matter if the die lands a 1, 3, 4, or 5. I'm just going to completely discard those cases. Just throw them out, not even consider them. And then that reduces to just as if the die only had 2 sides, a 2 and a 6, because we're ignoring the 1, 3, 4, 5. And the chance of a 2 or a 6 is now 1/2 each. So rather than trying to do the problem in the more complicated, keeping track of all the different ways the die could land, they just ignore the 1, 3, 4, and 5. All right, so that's the solution for Pascal and Fermat. Now, at this point, I introduced it last week, Friday, and you now have more skills working with probability problems, and it might seem easier to solve this problem. These folks worked for 3 years, not constantly, but they worked for 3 years solving this problem. and so it makes sense that it might take a little bit of work for you to figure out how to solve such a problem. I want to now switch to where we left off on terms of conditional probabilities. And just to review, the conditional probability is the notation for conditional probability is the probability that of A given B, where we read that the vertical line as the word given. So what's the chance that A occurs given you know that B has occurred? And that's the ratio of the probability that A and B occur, normalized or divided by the probability that B occurs. And if we simply rearrange the terms, we get what's called the multiplication rule, which is if you want to find out what's the chance that A and B both occur, that's simply the chance that A occurs times the chance that B occurs given A has occurred. So all I did was rearrange this, and I get what's called the multiplication rule. And by symmetry, the probability that A and B occur is the same as the probability that B and A occur. And so you could also write it as the probability that B occurs times the probability that A occurs given that B has occurred. So it can go in either direction. All right, let's look at another famous problem in probability, and that's Polya's urn. Polya's urn has 10 marbles in it. 4 are white and 6 are black. And they are indistinguishable except for their color. So if you reach into this urn and they're well mixed and you pick a marble, you don't know whether you're picking a black marble or a white marble. So you pick it out and you take a look at it. If it's white, you put it back and you add 3 more white marbles. If it's black, you put it back and you add 3 more black marbles. Okay, so the question is, how do I figure out if I see that the second marble drawn is white, how do I compute the chance that the first marble drawn was black? So I do this experiment, or this chance process, and I only tell you that the second draw is white. And I ask you, what's the chance that the first draw was black? So we can set this up with probability trees. So here's the tree. The very first draw, I could get a white ball or a black ball. And since there are 10 balls in the urn, I have 4/10, because 4 of them are white, I have 4/10 of a chance of getting a white ball, 6/10 of a chance of getting a black. Then the next round, now on the left-hand side, I have put back 3 more balls. So there are now 13 marbles in the urn, and I added white ones. And so I now have 13 marbles, and 7 of them are white. So the chance, if I look at this leftmost bottom outcome, the chance that it's white is going to be 7 out of 13, because there are now the original 4 plus the 3 additional ones. Is everybody with me? Yes, good. And the chance it's black is 6 out of 13. There's still 6 black. Now, on the other hand, if the first ball that I draw is black, I'm putting 3 more in that are the same color. So there will now be 9 black marbles. So the chance that I draw a black marble again is 9 out of 13. I multiply down the tree. Those are my conditional probabilities. Well, first I start with the probability the first draw is white, is 4/10, and then times the probability that the second ball is white given the first ball was white. That's 7/13. And I multiply down, I get 14 on 65. And I similarly do that for every single possible outcome here. So if I look at this one over here, the 27 over 65, what does that correspond to? What outcome does that correspond to? Yes? Oh, yes. Go ahead. Black on the first and the second. And I can compute that using the multiplication rule. That's essentially what the tree is doing. It's doing the multiplication rule. It's saying, okay, the chance that the first and the second ball are black is the chance the first ball's black times the chance the second ball's black given the first one was black. And so that's how I compute all these things. Next question. If I wanted to know what's the chance that the second ball is white, which of these events down here am I looking at? Yes? The 14 out of 65 and the other white one of 12 out of 65. And I can add those together to get the chance that the second ball is white. That's using another rule. I've forgotten its name. What's its name? The average conditional probability rule, which we'll get to on the next page. They all have rules, but the nice thing is if you draw the tree, you can reason it out, and you don't need to remember all these names. So that's the chance the second ball's white. Now, the final thing that we're trying to compute is what's the chance the first ball's black given the second ball's white? Now, here's where I use this notion of, well, that's the ratio of the chance that the first ball's black and the second ball's white. Well, the only place that happens is over here on the right, where I get a first ball black followed by a second ball white, and that has chance 12 on 65. Then I normalize it by the chance that the second ball's white. And we've already computed that probability. That's the sum of these two, 14 on 65 plus 12 on 65. Notice the really nice thing is the reason why I didn't bother to put this into, do the actual division and get the answer in decimals is because the denominators cancel. And so that's really nice, and I just get 12 over 26. So here's the solution, not using a probability tree, but using all of the notation with conditional probabilities. And it's the same thing. It's just sort of all written in terms of probability notation or mathematical notation. So if you can understand how a probability tree works, then you essentially get this. It might look kind of messy or cumbersome, but it's essentially what's going on with a probability tree. So if I want to know, first of all, if I want to know the probability the second ball is white, I'm just using this average conditional probability rule, which means I split that up into further possibilities. The second ball's white and the first ball's white, or the second ball's white and the first ball's black, because I know how to do those computations. Yes?
I thought that the first ball had to be black.
It does. I haven't gotten to that part yet.
Oh.
This is only the denominator of the, I'll get there. Yes, good point. This is only a part of the solution. So I'm just computing right now the chance the second ball is white, and I'm splitting that up into the two parts. The second's white and the first is white. The second's white and the first is black. And that's using what we call the average conditional probability rule, which in terms of our tree is simply multiplying down the tree and adding across the bottom. Okay, now we're getting to what you were asking, which is what's the chance that the first one was black? So this is the conditional probability. The first is black given the second is white, is our definition of conditional probability, which then we, to get the first is black and the second is white, we say, well, that's the first is black times the probability the second is white given the first is black. So notice what we've done is we've taken something that's really hard to compute, the first being black given the second's white. So that's not in our tree, and we've had to do work to get there. And we've been able to re-express it in terms of something that's easy to get from our tree. The second is white, given the first is black. And that's called Bayes' rule. So these all have names, but the idea is that you can figure these out through reasoning with the probability tree. So there's two ways to do it. One is to know these rules and apply the rules, and the other is to sort of derive them each time by using your probability tree. Oop. Wasn't sure that was, yeah. So are there questions on that? Because I'm now going to move to the next topic, which is still a probability topic, but this one is probability distributions. I want to make sure I don't. I'm going to skip ahead for a second just to give you a little interesting break. How many of you have heard of Paul the Octopus? Yes, in the back. Who's Paul the Octopus?
This octopus in Germany.
Uh-huh.
During the World Cup this summer was predict the outcomes of all the German games. Got all
Oh, wow, you know a lot about it. That's right. Paul, the psychic octopus, lives in an aquarium in Germany, and for 8 games, he was able to correctly predict the outcome of the games. And what did you think about Paul? Right. You weren't really sure if you thought he really was psychic. Somebody had their hand up. Yes? You think he's actually been given an invitation to the next World Cup, according to the news story I was reading. How's it? Well, so I thought you might be interested. I'm hoping this will work here. I realized I'm not sure if I'm on. Hang on. Let me make sure I got to get back onto CalNet. Let's watch Paul do his stuff. So here come these two acrylic boxes, one with the flag of Uruguay, one with the flag of Germany. You can see in the very bottom, there's a little treat for him. It's either like a mollusk or something. And there's Paul. Now, they have lids. There's all the news media. Here he is. And he has to take the lid off of the box. And you can't hear it, but there's an immense amount of hubbub going on as to, is he going to go for Germany or Uruguay? And there's spectators with the German flag, and there he goes. He gets the lid off, and you see that tentacle down in there is going for, and he eats the German crustacean or whatever. And so that's his prediction, is that Germany will win. And Germany did win. And he made, there were 7 games in which Germany played, and he made the prediction correct every time. And then he also made the prediction correct for the final round as well. And it's true, he has received death threats, which say something about poisoning the aquarium, in which, yes. That was when he, in particular, that was when he predicted that Spain would beat Germany, and they were not happy about the prediction. So what we're going to be doing is actually looking at that from the point of view of, well, what's the chance that could happen? So you can keep that in the back of your mind as we work our way through formalizing computations probabilities. So essentially, so far we've simply been working with computing probabilities through different techniques. The trees, enumeration of all the possible outcomes, symmetry, complements, etc. But a lot of probability problems fall into problems that are of the same type, in which we can easily compute their probabilities. And these we call recognizable distributions. Or even if they're not recognizable distributions, there are ways to summarize the probabilities of all the possible outcomes. And there are 2 essential ways at least with discrete probabilities. The first one is to have a distribution table. And by that we mean a list of all the possible outcomes or values that could come out of this chance process, and associated with each value the chance that it would happen. The second way is if there's a rule or a function that will compute the chance of something happening. So we're going to look at both of these. So first, if we go back to the problem we saw last Friday, where we were drawing 2 cards from a deck, 2 cards without replacement. And if we ask the question as to how many hearts are in those first 2 draws, we know now that we could list all the possible outcomes. We could have 0, no hearts in the first 2 draws, 1 heart in the first 2 draws, or 2 hearts in the first 2 draws. And then for each one of those, in our table, we have the chance that happens. So we did these computations last week. We said, for example, that the chance that there are no hearts. Oops, you know what I did? I did the computation for red and black, and then I changed the problem to hearts. And so my probabilities are not right. So we can either switch over to talk about red and black, or how about this? We can instead change the chances to the right ones. Let's get you guys to change the chances. Did you all recognize that those were wrong? Yes, good. And nobody said anything. Okay, so for those of you who nodded your head yes, I'm now looking for you to give me the chance that no hearts were drawn. Chance that no hearts were drawn, 0. Well, the denominator's right. It's 52 times 51. Those are all the possible ways of drawing 2 cards. It's the numerator that's wrong. Yes? Is it 39 times 38? Where'd you get the 39 from?
Well, I know that each suit has 13 cards, and since we're getting rid of one,
Mm-hmm.
or one suit, then it's adding your 2.
So each suit has 13 cards. There are 4 suits. 3 of them are not hearts. So 3 times 13 is 39. And so to not get a heart on there are 39 times 38 ways to not get a heart. Very good. That's the answer to the first one. The answer to the second one, not the second, let's skip down to the bottom. What's the chance you get 2 hearts? Can we use the same logic? You have to get 2 hearts. There are 13, so it's 13 times 12. So the chance of 2 would be 13 times 12. How can you easily get the chance of 1 from that without doing many more computations? Complement rule? You know these have to add to 1, right? We've now figured out the chance of 0 and the chance of 2. We could just say, well, that's 1 minus the chance of 0, subtract the chance of 2. So it would be 1 minus 39 times 38 over 52 times 51 minus 13 times 12 over 52 times 51. That's one way to do it. What's another way to do it more directly? How many ways can I get a heart and not a heart? 2, meaning I can get the first one's a heart, the second's not, or the first one's not a heart, the second one is. Good, okay. What's one of them? What's the chance the first is a heart and the second's not? Yes? 13 times 39, right, over 52 times 51. That's right. And then the other way around would be 39 times 13 over 52 times 51. They're the same. So I could just say it's 2 times 13 times 39 over 52 times 51. So if we just change those, the 2's correct, but the 2 26's are not, those should be 13 and 39. Good. All right. Here's another problem where we roll a die 3 times, and I simply want to count the number of 1s and 2s that I observe in those 3 rolls. So if I reclassify these as S being success for a 1 or a 2, then there are now, again, if I'm trying to compute these probabilities, there are now 4 possibilities. I get no 1s or 2s, I get 1 or 2, 2 1s or 2s, or 3 1 or 2. It's much easier if I just change that to be S for success. So I'm defining a success as rolling a 1 or a 2. So I could get no successes, 1 success, 2 successes, or 3 successes on my 3 rolls of my fair die. And so I have now enumerated these. There are 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Are they all equally likely? And therefore, each one of those possibilities has a chance of 1 over 8. Aren't there 8 possibilities? Oh, yeah. Yes, but I've reduced it to S or F. All right. So there are 8 possibilities. What do you think? So is the chance of 0 successes FFF 1/8, and the chance of 3 successes SSS 1/8, because I have 8 different possible outcomes? Yes?
No, because you have more chances of getting failure.
You have more chances of failing than succeeding because?
Because there's more numbers of people involved.
That's right. There's more. A 1 or a 2 is a success, but a 3, 4, 5, or 6 is a failure. So you're more likely to fail than succeed. In fact, can you tell me what's the chance that you succeed on any one roll? Did you say yes, 1/3? And the chance you fail on any one roll will be 2/3. So it's FFF is far more likely to happen than SSS. So, and we can do that computation. If you want, you can put in your head a probability tree, but it's starting to have 3 layers of branches now. Success, fail on the first toss, and then for each one of those, success, fail on the second toss. For each one of those, success, fail on the third toss. Or we can just do the computation using conditional probabilities. And here we go. This is the first one. The probability of 3 successes is the probability of SSS. If we think in terms of what that tree is, it's saying, okay, what's the chance of success on the first toss of the die? Then, given a success on the first one, what's the chance of a success on the second? That's working our way down the tree. Then, given a success on the first and the second, what's the chance of a success on the third? So we do have that probability tree we could in our head, and that's the computation that corresponds to working our way down the branches. Now, the nice thing is this collapses to be something very simple. The chance that the second is a success, given the first was, doesn't matter if it's a success or failure. Those rolls or the die are independent of each other. What happened on the first round doesn't affect what happens on the second. What happens on the first and second does not affect what happens on the third. So it's always a third, no matter what's happened in the past. The chance of a success will be a third. And so that's just a third times a third times a third, or 1 in 27. Is everybody with me? Now let's try the chance of 2 successes. We saw that there are 3 different ways to get it: SSF, SFS, and FSS. So a failure on the last round, or the middle round, or the first round, and the other 2 being successes. Any one of those, we start with the first one, would be a chance of success on the first round is a third. Success on the second round, a third. Failure on the third round, 2/3. That's the first computation in the middle. Now the chance of success followed by failure followed by success would be a third for the first round. And now in the second round, failure is 2/3. And then on the third round, success is 1/3. And then finally, fail the first time, succeed the next 2, would be 2/3 times 1/3 times 1/3. Notice that they all have the exact same probability, each one of these. So I could collect them together and say it's 3 times the chance of any one of them. So it's 3 times a third squared times 2/3. Have you all seen this before, maybe in high school? I know that statistics and probability is sort of taught to you now throughout your entire high school curriculum. You see it in algebra, you see it in geometry, you see it in pre-calculus. So maybe you've seen this before? Maybe? Here's a complete probability table for each of the possible outcomes: 0, 1, 2, or 3. Now that we know how to do these computations, we can do them pretty quickly by, yes, we do need to know how many different ways to get any particular one. So let's take 1 here, probability of 1. That's 1 success and 2 failures. There are 3 ways to get it. We know that each one has the same chance, and that's the chance of any one of them is 1/3 times 2/3 squared. And so that's 12 on 27. So I've got the computations for each one of these. Chance of 3 successes, 1 in 27. The chance of no successes was 8 over 27. So it's exactly what our intuition told us. It should be far more likely to fail 3 times than to succeed 3 times. Questions on that? So here's the general formula for this particular example with 3 trials where the chance of success on any one trial is 1/3 and failure on any one trial is 2/3. The chance of k successes, for k being either 0, 1, 2, or 3, is the number of ways to have k successes times the chance of any one of them, because they all have the same chance. So that's 1/3 to the k, that's the number of successes, times 2/3 to the n minus k, that's the number of failures. All right, this then can be formalized into what's called the binomial distribution. So when I started this little mini discussion on probability distributions and say we can use tables to summarize a distribution where we have each of the possible outcomes and each of the chances connected to those outcomes, sometimes there are, we name those distributions and produce rules like this rule for actually doing the computation, and we generalize it a little further. This often happens, this arises in statistics when we're dealing with data, and we've got nominal data or ordinal data, and we want to count up how many occurrences there are of a particular level of a factor. How many underweight babies are there? How many children with polio are there? How many times does Paul the octopus correctly predict the outcome of a World Cup match? So this particular distribution arises a lot. I should back up and say the children with the polio is not quite the binomial distribution, but we'll get there. It's close to it, but not quite. We'll talk about that distribution. So we've already talked about Paul the octopus. Here he is again, taking the lid off of the acrylic box with the German flag. And at this point, I want to ask you guys, there's the YouTube link. I want to ask you guys, what do you think about this? What do you think? So we can you, first of all, can you fit it into a binomial distribution? Can you say, how would we, so we'd like to formalize it, but even before we formalize, I'd just like to know your reactions to this. Yes?
Paul the octopus started out closest to the German flag box.
Paul the octopus started out closest to the German flag box.
So
that's right.
It seems unreasonable to say that, well, there was a 50-50 chance of Paul the octopus picking which box.
Really good point. I thought about that as well. And they actually purposely kept the order the same according to which was ranked as more likely to win or not. And that determined the order. And if Germany was always on one, Germany didn't always win, obviously, right? But if, yes, I'm with you there. Yes? The color, yes, it turns out that an octopus is colorblind, but the pattern and the intensity in the colors of those flags, you now know there's this issue about intensity as well with colors, are different. And maybe he's attracted to certain stripes or that sort of thing. What else makes you somewhat? So we could formulate this and do a computation, which we're going to do. But the real issue then becomes, do you actually think that, which is a point you were making, do you actually think that this exercise that Paul the octopus is going through really fits into this notion of independent, identically distributed trials or not? So here's how we could do those computations. There are 8 trials. He made 8 predictions for the game. The chance of success is 1/2. And this is, as we said, might be debatable. If the lead one is always in the right-hand bucket and he's always coming from the right, maybe the chance of success is greater than 1/2. What's the chance of 8 successes? So it's like our dice rolling game, except now it's opening up these acrylic boxes with food inside of them. There's only one way to get 8 successes. And if we believe in this notion that it's independent and they each have a chance of 1/2, which we're somewhat doubtful of, That would be 1 over 2 raised to the 8th, and 1 out of 256. So here's some other information I found when I was looking at Wikipedia. It's amazing what you can find on Wikipedia. But there was also Leon the porcupine who tried to predict the outcome, and Petty the pygmy hippopotamus, Jimmy the Peruvian guinea pig, Anton the tamarin, Manny the parakeet, Pauline the octopus from Holland, Zhaozha the octopus from China, Pino the chimpanzee, and it goes on. All of these tried to predict outcomes as well, and they were not perfect. So that must mean Paul the octopus is really special. Is that what you draw, the conclusion you draw from this? Yes? You think they got motivated. They got inspired by Paul the octopus. How about this? What do you think? That there are all these, this is only 10 or 11 that I found on Wikipedia, of animals in zoos that were like, they were the, one of them was fed a little raisin and the others were fed, whatever kind of food, they were fed their favorite foods, and whichever one they picked was their prediction. Somebody had their hand raised over here. Yes?
Well, I was going to say, you said that you only found 10, or that you believe that this is just 10, and that there's like a whole bunch of other ones. And if the prediction is that 1 out of 256 out of 256, one person's going to get it right 8 of the time, maybe Paul is just not one.
I like your logic. In the back. Yes, that's the same idea as what you were saying, I believe. So when you put it in this bigger context of knowing that there are animals in zoos all over the world who are being subjected to predicting the outcomes of the World Cup, then it's like, well, Paul just got lucky compared to, it is possible that if you had 256 animals in zoos around the world all predicting the outcome for 8 games, that you'd expect one of them to get it right. So even for just these 11 animals, the chance that at least one of these 11 animals, so now we're extending this actually to another binomial problem. So this is a shift. So instead we think of Paul the octopus, Pauline the octopus, whatever, these other, Manny the parakeet, etc. Each one of those has a chance to get 8 right. And if it really is at random, they each have a chance of 1 over 256 of getting them all right. And now we've got 11 trials with a probability of 1 over 256 of succeeding. Do you see that switch? Where every animal is like a trial. And a success is getting all 8 of those predictions right. And the chance that that would happen is about 4%. So all of a sudden it doesn't look quite so rare as 1 in 256. It's now down to 4 out of 100. And if you actually had the animal that got it wrong every single time, that would be a good way of predicting as well. If you include either one of those possibilities, that's about 9%. So then all of a sudden, Paul's not looking quite so special anymore. Maybe he just, and that's just purely under the assumption that all of these things really are independent and equally likely, which Warren made the point of at the beginning, and I agree entirely, is like, well, it's pretty hard to know, given the setup of that experiment, whether or not it really is equally likely and independent each time.
Even if it was 1 out of 256 and he was the only octopus that ever underwent this experiment, we have to consider the probability that an octopus that's this big really actually knows the future. What's the probability of that compared to 1 out of 2?
Yeah, so you get to, there's this whole study, there's a whole branch within statistics of people who study this kind of thing as to, not for octopi, but for people, as to whether there is this paranormal perception. I don't even want to go there, but yes, that's a very good point. And I will say one other thing about Paul. 2 years ago, he didn't do a very good job. They actually have the data where he made 6 predictions and only got 4 of those 6 right. Maybe he's getting better. All right, so now let's just sort of, I want to wrap this up in terms of what the general terminology is. We have a binomial distribution. That's a kind of a probability distribution. It has some very specific characteristics. The idea is that there are a certain number of trials, and these trials are independent of each other. So how many? We have, I'm now generalizing it, there are n trials. And on each trial, there's the exact same chance of being successful. And that is a probability p of being successful on any given trial. And the trials are independent of each other. So being successful on the first trial doesn't affect success on the second or the third or the fourth or the nth trial. Then we ask the question, what's the chance of k successes? What's the probability of k successes? And we can produce a rule for computing these. Here's the rule. Probability of k successes is n choose k, that's how we read that, n choose k. That's the number of ways of getting k successes and n minus k failures, times the chance of any one of them, which will be p to the k, that's the probability of a success k times 1 minus p to the n minus k, and that's having n minus k failures. Just to remind you, I'm sure you've all seen this before, but just to remind you, n choose k is n factorial divided by k factorial times n minus k factorial. And to remind you what k factorial is, there should not be an exclamation point at the end there. It's k times k minus 1 times k minus 2 times ... 2 times 1, no exclamation point. So 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And by definition, 0 factorial is 1. So that's the binomial distribution, and we'll see it lots of times in many of our statistics problems. The other distribution we see is the hypergeometric distribution. I want to wait until Friday to show you that. And the other thing we're going to do on Friday is in R, there are a lot of wonderful built-in functions to compute these probabilities, to generate random observations from these probability distributions, and to simulate from these distributions. So we're going to spend a good chunk of Friday looking at these various functions in R and how to use them. See you all Friday. And for those of you, I all heard that there's no quiz tomorrow.